Hey everyone, welcome. Have you ever actually stopped to just marvel at the profound, invisible mysteries that unfold right in front of us literally every single day? In this explainer, we're taking a look at one of the most fundamental forces out there, the invisible glue that literally holds our reality together. We're going to explore exactly what keeps the cosmos in check and unlock the secrets of Newton's law of universal gravitation.
Let's start with an everyday mystery. Really think about it for a second. The Earth is this incredibly massive object, and it's constantly spinning on its axis at a crazy rapid pace. Yet, here we are just standing on the surface. Why don't we just float away into space? Why are we stuck to the ground, moving perfectly in sync with a giant spinning globe? And if you drop something, it doesn't fall to the left or the right or, float upwards, it drops straight down. Always.
The mystery kind of deepens when we look up at the night sky, right? The moon travels around the Earth in a nice circular path. But in physics, we know that for any body to maintain a circular path, it requires a centripetal force constantly pulling it toward the center. But there's no physical tether connecting the Earth to the moon. So what exactly is providing that centripetal force across the totally empty vacuum of space? Okay, let's dive into this. Because the answer to all of these questions comes down to one absolutely incredible concept brought to us by Sir Isaac Newton. The famous story goes, right? Newton is sitting under a tree, sees an apple fall straight down, and wonders, why straight down? Why not sideways? And that simple observation led him to propose a completely groundbreaking theory, Newton's law of universal gravitation. He realized this isn't just about apples or planets. The law states that every single body in the universe attracts every other body with a specific force, which we call gravitational force. You, the Earth, the moon, the apple, literally everything is pulling on absolutely everything else. To figure out exactly how strong that pull is, let's look at Section 1, the mathematical formula, rules of attraction. Newton didn't just hand us a neat conceptual theory, he gave us a precise mathematical formula. Let's break it down real quick. F stands for the gravitational force. Newton said this force is directly proportional to the product of the two masses involved. So you take mass 1, multiply it by mass 2. The bigger the result, well, the stronger the force. But he also figured out that distance matters immensely. The force is inversely proportional to the square of the distance between their centers, which is represented by r squared. Put simply, as objects get farther apart, the attraction between them drops off significantly. Now, to balance this equation, we introduce a constant of proportionality, represented by the capital letter G. This is the universal gravitational constant. Just think about this number, 6.67 times 10 to the power of negative 11. That negative 11 means you literally have a decimal point followed by 10 zeros before you even hit the very first digit. It is an incredibly, almost unfathomably tiny number. So the crucial point is, this explains another major mystery. If absolutely everything attracts everything else, why aren't you violently pulled toward the desk you're sitting at or, the furniture in your room? Well, it's because G is so incredibly minuscule. Since the force depends on multiplying your mass by the furniture's mass and then multiplying it by this impossibly tiny constant, the resulting force is virtually zero. You need at least one incredibly massive object, like an entire planet, like the Earth, for the product of the masses to be large enough to actually overcome that tiny constant and create a force you can feel. Now, the unit for G might look super complex, but there's a really elegant way to understand it without having to memorize anything for your exams. Just isolate G in our formula. Move the distance squared over by multiplying it with force, and divide by the two masses. Force is measured in newtons, distance squared is meters squared, and the two masses on the bottom give us kilograms squared. Bring it all together, and the unit derives itself, Newton meter squared per kilogram squared. Just a beautiful piece of mathematical logic right there.
But gravity isn't exactly like the other forces in physics. It really has its own specific personality. Moving on to Section 2, key properties of gravity. Let's run through these properties and see how they build a complete picture. First, gravity is strictly an attractive force. Think about electrical charges or magnets. They can attract, sure, but they can also repel. Gravity never repels, ever. Second, it is completely independent of the medium. Whether there's air, water, a solid brick wall, or the total vacuum of space between two objects, the gravitational force between them doesn't change one single bit. Third, its line of action is perfectly straight. It acts strictly along the invisible line joining the centers of the two objects. And finally, mathematically speaking, this law is valid primarily for point masses. Now, this doesn't just mean tiny specks. Even the Earth and the Moon are considered point masses here because their actual sizes are very small compared to the massive distance between them. Okay, so this brings us to a concept that trips up almost everyone when they first explore this law. Section 3, demystifying the inverse square rule. Newton didn't just blindly guess that the distance should be squared. Actually, this was a massive experimental mystery he had to solve by meticulously looking at real-world data to figure out exactly how the force faded as objects moved apart. Let's imagine a quick scenario to understand what that data showed him.
And this brilliantly illustrates the reality of the inverse square law. Imagine at a distance of 1 meter, the force between two objects is 36 newtons. Logic might kind of tell you that if you double the distance to 2 meters, the force should just cut in half to 18 newtons. But the data shows it actually plummets to just 9 newtons, a quarter of the original force. If you triple the distance to 3 meters, it doesn't drop to a third, it drops to a ninth, just 4 newtons. The force diminishes based on the square of the distance, 1 over 2 squared, 1 over 3 squared. The math perfectly maps to the physical reality.
So, to bring all the pieces of this giant puzzle together, we move to Section 4, connection to Newton's third law. We all know Newton's third law states that every action has an equal and opposite reaction. In the context of gravity, this means the force is entirely mutual. Because the formula relies on the product of both masses together, mass 1 times mass 2, it actually doesn't matter which object is bigger. The Earth pulls the tiny apple downward with a specific force. That's the action. The absolutely incredible reality here is that the tiny apple pulls the massive Earth upward with the exact same magnitude of force. The forces are perfectly equal and perfectly opposite. But that leaves us with one final, fascinating puzzle to ponder. If the apple pulls on the Earth with the exact same amount of force that the Earth pulls on the apple, why do we only see the apple falling down and not the Earth rushing up to meet it? I want you to think about the relationship between mass, force, and acceleration. I'll leave you with that thought-provoking mystery. Thank you so much for joining me on this explainer today. I really hope you walk away with a much deeper appreciation for the invisible glue holding our universe together. Keep wondering and keep learning.